So far, everything we've talked about has been based on Taylor series expansions of the type that we know about from calculus. If we truncate the series, only include a finite number of terms, n terms in this case, this will be the Taylor method of order n. Of course, the first order Taylor method, in which you only include terms out to delta t to the first power, is nothing but Euler's method, as we've seen before. In principle, it's a simple matter to write out the second order Taylor method. We include all of the terms that were in Euler, and we also include 1/2 factorial times delta t squared times the second derivative of y with respect to t evaluated at the current point ti wi. But now we start having a problem because this second derivative of y with respect to t is the derivative of dy dt, which is the derivative of a function that depends on two things, one of which is a function of t. We figured out the other day that the appropriate derivative to write down would be this quantity. Of course, in our differential equation, dy dt is f of t and y, so we could write it in this format. In principle, you could write out the third derivative of y, the fourth derivative, and so on, and get higher order Taylor methods, but the actual calculation of these derivatives becomes painful after a while. By using multivariable expansions, though, we saw that if we're clever, we can emulate these Taylor methods of higher order with methods that only involve function values. The ones that we worked out by hand was this method. This is roughly as accurate as Taylor 2, but I'm not required to differentiate the f function in any way. I'm only required to calculate f values, which is easy to do if you know the differential equation. If you were to figure out to the fourth derivative of y with respect to t, and then use our multivariable expansion again, you would be able to convince yourself that the following algorithm is going to emulate Taylor 4 without ever having to do any fourth derivatives or third or second or even first derivatives. Let K1 equal the time step times f evaluated at the current point TIWI. Let K2 be delta t times an f value, except you're going to evaluate the first variable at the current t value plus half of a time step, and the other position is going to have the current y approximation plus half of K1. K3 is delta t times f evaluated at that same t value, but at a different y value. Here you'll use w plus 1/2 K2. K4 is going to be delta t times an f value. This is going to be a full time step ahead of where I am at the moment. And in the second slot, you write down wi plus K3, the current approximation to the solution, plus this K3 quantity. If you let wi plus 1 be wi plus 1/6 of K1 plus 2K2 plus 2K3 plus K4, then this method is going to be called the Runge-Kutta method of order 4. If we apply this method to the same sample problem that we've been using, That is, dy dt is supposed to be t cosine t plus y over t, and y at 1 is supposed to be sine of 1, t being between 1 and 6. We showed the other day that the exact solution is y equals t times sine t. Having a new numerical method, we can try that method out on our sample problem. In all of our sample problems here, I'm going to use 100 subdivisions in the interval between 1 to 6. And rather than have you look at the numbers from the code, I'm going to just present them here. I'm going to look early in the calculation, near the middle, and towards the end. For Euler's method, early on, the error was about 10 to the negative 2. Towards the middle, it got sort of bad. It was about 0.19. And at the end, it was back down to 10 to the negative 2. The fact that Euler is not very accurate shouldn't come as a terrible surprise to us because it's a simple method. If we do Taylor of order 2, things are improved. The error early on is 10 to the minus 3. Near the middle, it's still about 10 to the negative 3. And it actually gets better at the end, being roughly 10 to the negative 5 towards the end of the calculation as t is getting close to 6. Third order Taylor is even better than that. And the Runge-Kutta method that we've just discussed, early on, the error is about 10 to the negative 8. Near the middle, it's still about 10 to the negative 8. And towards the end, it's not much worse than that. So for this particular problem, Runge-Kutta 4 is an obvious winner. In view of the fact that we're going to have a whole bunch of other methods rather than just these, a person might well think to themselves, why would you ever need a method other than Runge-Kutta 4 here? We'll see about that in the next discussion. For now, we're just looking at methods. Each of these methods that we've talked about compute wi plus 1 using only information involving wi. Another idea, completely different one, is if I'm computing w number 7, I'll obviously need to include some information from w number 6, but why not pull in some information from w5 or 4 or 3? Why not have a method that isn't just going from one time value to another using information at the starting time value? Why not use multiple values that you have previously obtained? These sort of methods are called multi-step methods. I want to talk about the simplest of all possible multi-step methods. So I'm going to imagine that not only do I know the value of the solution at t0, but I also know the value of the solution at t1. This may be given to us in a problem, or we may use some accurate method like Runge-Kutta 4 in order to get a good approximation for y1. After that, we're going to use W0 and W1 to get an estimate for W2. We'll use W1 and W2, which we just figured out, to get an estimate for W3. Then we'll use W2 and W3, which we just figured out, to get an estimate for W4, and so on. Based on earlier discussions, it must be true that the true solution at time I plus 1 is the true solution at time I plus the integral from ti to ti plus 1 of f. I can't use the letter t in here or I'll get confused. I'll use u and y with respect to u. We're going to interpolate something. We're not going to interpolate the y, though. We're going to interpolate the f of t and y. What we'll do is we'll find an interpolating polynomial that gives the same value as f does when the time value is ti minus 1 and ti. And in this integral that we have to do, we will use the polynomial instead of the unknown actual function. And this is how we will approximate this. This is what's going to turn the y numbers into w numbers. Writing out the polynomial is easy if we remember the Newton form. These are just function values, and these are this number minus that number divided by that number minus that number. The number on the bottom is delta t. Our polynomial that we're going to use, polynomial as a function of u, is this constant plus that constant times the variable minus the smallest of the first coordinates out of my data set. As a result, this integral that I need if I want to move forward in time is going to be approximated by the integral of its interpolating polynomial. As a result, wi plus 1, my approximation at I plus 1, is going to be the approximation at ti plus the integral of that first term is easy to do. It's the integral of a constant. So it's the constant times t. You evaluate at ti plus 1 and ti and subtract. The first term has an integral that's easy to describe. It's fi minus 1 times delta t. In the second term, the ugly-looking fraction is just a constant, so I can pull it out of the integral, and what's left is easy enough to integrate. An antiderivative is 1/2 u minus ti minus 1 squared, evaluated between ti plus 1 and ti. After all the arithmetic and algebra is finally done, you end up with 1/2 times 3 times delta t squared. This is the value of this integral. Putting all the pieces together, wi plus 1 is w at I time I plus the easy to calculate term times this rather ugly looking coefficient times 3/2 delta t squared. If you'll notice, a factor of delta t will cancel out. So after doing some algebra, it turns out that w number I plus 1 is wi plus delta t over 2 times 3/2 of the f value at time ti minus the f value at time ti minus 1. The final result of all of this is wi plus 1 is wi plus delta t over 2 times f. We will write it out in full now. Ti wi minus f at ti minus 1, wi minus 1. Your textbook calls this the Adams-Bashforth two-step explicit method. It also lists formulas for the 3-step method, the 4-step method, and the 5-step method as well. We won't be deriving those. It's straightforward, but extremely tedious. It's all based on interpolating polynomials. One minor point, you are supposed to have W0 and W1 supplied to you in some way. for this to work. So this means that the first W that you're actually going to calculate will be W2. So at the beginning, I want I plus 1 to be 2. That means that the I needs to start off as 1 in our program. Depending on which method you're using, that number may change. But for this one-step atoms-4th explicit method, you start at 1. In the next meeting, we will talk about how to program such things. Also, we'll look at another class of methods called the atoms Molten implicit methods, in which we do the same sort of thing, but we also include the possibility of including the point that we don't know in the set of interpolating points, which at first glance sounds crazy. Between now and then, if you get a chance, go back and look in your notes about the fixed point analysis, how to calculate fixed points of functions using fixed point iteration, and make sure you know the answer to this question. Under what circumstance does xk plus 1 equals g of xk guaranteed to converge? In the meantime, I hope everyone's having a good day. I'll talk to you again later.